POPs are finally available in the official version of TouchDesigner, and we're going to build a gravitational system today. So there's a central point right here, a central mass, and all those particles, which are instanced as boxes, are falling towards this central point, but because they have an initial velocity, they actually fall around that central point or potentially spin off to the void, or might also fall into the center. So kind of like in our solar system or something. So that's what we're going to build today. And I was actually planning to show this in the workshop I was supposed to give at the Bright Festival in Leipzig. But unfortunately, I got ill, so I wasn't able to do it there. I was really happy to have Markus Heckmann giving the workshop instead. And yeah, now I have the opportunity to explain to you in this online tutorial how you can build this in the all-new pop operator family. Little spin-off, I was actually planning to show you how you can use POPs to build a fabric simulation without any GLSL now in TouchDesigner. It would have been possible in TOPs before, I'm sure, but it's already easier now in POPs, and it is more flexible because you can input basically any input geometry that is a meshed surface. But here's how it turns out. So it's really convoluted. We have all the substeps here, and we have all the spring forces, which by themselves contains a lot of math here. And then I decided, well, this is probably not going to be a fun tutorial. Maybe I will release a fabric simulation tool, but this is not what we're going to look at today. We are going to build this gravitational system. So yeah, I would say let's get started. I will delete everything we are having here, and we will start from scratch so you can follow along. If you haven't used POPs yet, POPs are basically the new SOPs in a way, as in there's a lot of stuff that we could have done in SOPs before, which is now available in POPs. But POPs have the advantage of being calculated on the graphics card, on the GPU instead of the CPU. And they can take advantage of the parallel architecture of GPUs and hence be way faster than SOPs if you use them right. And yeah, if you've been familiar with SOPs, or you've used maybe Houdini or a different kind of 3D tool before, you might be familiar with the fact that any geometry is often represented as a collection of points that we have right here, and then potentially triangles or other kinds of primitives like rectangles, like quads, or lines, or some kind of geometry between those points. And those points are certainly a numbered list. So here's point 0, there have point 1, etc., etc. And we actually also have vertices, which are basically an assignment of points to the primitives. So this is the structure we have for any POP now. It's basically the same as it was for SOPs. And if we use a POP to DAT, we can have a look at, here I'm now extracting the points, and we could extract the vertices and the primitives as well. And we can lay out what we see illustrated here as the raw data. And you will notice that while we're working with POPs, it's all about attributes and manipulating those attributes to move around the geometry or alter it and create it. So attributes is going to be a super relevant term. And an attribute is basically a value that is assigned to each of these entities, or to one of those entities. So either we are going to have attributes. Attributes can either live on the points, the primitives, or the vertices. And if I middle mouse click on any POP, we can get the overview of this POP. We will see how many points there are, how many primitives, which are all triangles in this case, how many vertices. We also actually have a dimension which is not going to be relevant today. It's bounding information. And we are going to have a list of all attributes. This is what I wanted to talk about right now. So we do have 2 point attributes. One is called P for position and the other one N for normal. And we do have one attribute that is assigned to the vertices, which is called text. So this is what you might know as UV coordinates. We could also have an attribute living on the primitives. So for instance, if we were to assign a random color, right now I assigned the color to each point. So it's interpolated for each, over the surface, it's interpolated. But if I would assign this attribute not to live on the points, but on the primitives, we would see that now, and let's update this here to the primitives. So this is extracting the primitives from that pop, and you can see there's a color attribute that is now has 1 value per primitive, and hence each primitive has a constant color now. So if you think about pops, think about attributes, which we are going to alter. And yeah, to get started with the actual patch we are working on, let's start by generating a point cloud. You can always use the point generator for this. You could also use a point file in to maybe load a specific point file. This is a banana, for instance, or start somewhere else. But let's start with the point generator. This is going to generate a bunch of points for us in a given shape. Let's start with a circle. And you can see that if we middle mouse click here, again, we have a position and a normal. And on the lower left side, left hand of pop, you will always see which attributes have been created or altered by this very pop. So in this case, it's position and normal. And what we will do, we are going to change the positions and we'll introduce some other attributes in between here. But to first lay out the overall patch, we will then go ahead and use the current positions of our particles and a CopyPOP to copy boxes. So the CopyPOP takes 2 inputs, one input geometry that is then copied to each position to each point in the second input. So now we have a lot of boxes here. They are so overlapping that we can't really make up any individual boxes. But we'll work on that in a minute. And then we are going to render this in a geometry node together with a camera. And we will use some light as well. And we're going to use a render top. And that's going to be our final output, which I'm going to display in the background. So this is basically, in here we are going to build the particle system. This is our layout. Let's change some stuff about the rendering pipeline. I will set the resolution of the render top to monitors 0.width, width and respectively height, such that I'm rendering at full screen resolution. I will go to the camera and set its background color to have alpha 1, such that we don't see the checkerboard grid. And now we can, decide to render this. And on this default torus, I will right-click here and connect the geometry directly to this. And that will, drop my FPS down. So I'll pause my playback. But now this has created an in and out pop inside of the geometry and renders and displays what I've inputted into the geometry. But yeah, this is too expensive at the moment because we are having 10,000 points and we are rendering those big boxes on them. So maybe as a first step, we should, let's fix this to only be 100 points, then my frame rate doesn't drop. And then we can introduce the first new attribute, because I want all those boxes to have varying sizes. Right now they're all of the same size, and we could argue that the size is too big, but especially I want those to be different for each point. And I want those to be random, to be specific. And here we have a new pop, which we haven't used yet, which is the RandomPOP. And we are going to randomize the point size. So let's give it a proper name. And the RandomPOP comes, it's an amazing pop where you can choose all kinds of randomness. We're going to uniformly create our point sizes. The point size is going to be only one float value per point. So we should choose random size 1. Then the seed for our random number generator should be different than the seed that we used on the point generator, which also has a random number generator and a certain seed, because otherwise you might get some unexpected patterns in your randomness. So let's use a different seed. And yeah, the parameter size is also 1, and we are going to have maybe point sizes between, let's start with some values. We can iterate those later, but we want to have small boxes. And I'm going to not add this random value to an existing attribute, but I will set a new attribute to this value. And as an output attribute scope, I can now decide what that attribute should be called. And I could, give it my own name here, but we can actually use this dropdown to choose one of the kind of common attribute names that TouchDesigner works with. So TouchDesigner knows about color and point size, line width, and texture. So these are and position and normal. These are kind of the common attributes, but we can always also work with custom ones. Let's use the point scale, because this is what point scale is supposed to be used for, kind of. So now this pop has a little indicator down here that we've introduced and changed a new attribute called point scale, which is passed down this network. And in the CopyPOP, we can actually go to the template page and say that we want to template scale our geometry using a given attribute. And here we could have chosen any attribute name that exists in the input, but we work with point scale, so let's also use that. And now we do have way smaller boxes. We can go back to larger amount of boxes if we feel like it, without our frame rate dropping. And we do see that they are of varying size because we've randomized the point scale. I do not like that the light is shining on those boxes from the front. I want to reposition my light a little bit to the side. I've just chosen some basically arbitrary numbers right here. But maybe I want the light to be looking at my geometry. So I just dragged and dropped it here and chose it as the look at component. And I'm going to change my light type to be a distant light. And I actually want to use soft shadows and set a proper resolution here and increase those quality values a bit. But we actually don't really see any result of this yet, because our boxes are kind of, well, here we do see some of the shadows, which is already nicer, but all those boxes are aligned along the same axis at the moment. They are not rotated in an interesting way. And I kind of don't like that. So as a next step, I want to rotate those boxes randomly. And if we have another look at the CopyPOP, we see that it has a built-in template rotate option. And if I turn that on, it's looking for an attribute called rod. Again, we could give it any name, but rod is reasonable, I think. So let's create a new random attribute. So again, this is going to be set to a new attribute called rod. And this time we actually want a random size of 3, but a parameter size of 1, because for all 3 dimensions we want the same parameter range. from 0 to 360, as in these are degrees. And here is actually a little bit of that structure I talked about, so we should use a different seed again. And this is going to be our random rotation. Yeah, and our rod should have three. Sorry if this was a little bit quick. Potentially, what have I done here? I clicked on those two little arrows and chose, because if I don't do this, we might see that rotation is already for 3. Oh, maybe it wasn't necessary to do this. It already was based on the random size, it chose to set up the rotational attribute as a float 3. If I would have chosen this to be only one-dimensional, it would be a float. So, and you could explicitly set this the number of components in this little menu down here, but we don't really need this. Okay, so if we have a closer look at the boxes now, they are all randomly oriented, and that's what I was looking for. Good. Okay, but they are all static, and let's go ahead and create an interesting behavior of those boxes. In the world of tops, you might be used to feedback loops, and we do have a beautiful FeedbackPOP as well, and we can like quickly set something up here. So if we were to use a feedback, we could introduce some noise to the, in this case, positions, because we add the noise to the positions by default. We should potentially do this by a really small amount. So let's say 1/60, which is our frame rate. And if we create a little feedback loop right here, we would immediately see an interesting behavior of those boxes. And this is what we want to build after all. We want to have some kind of feedback loop, but POPs now come with a very interesting new operator. Well, all those operators are new, but a new concept, which is called a ParticlePOP. And this is basically a feedback loop on steroids for particle systems. So if we connect this here, you will see that the ParticlePOP immediately created a whole lot of new attributes for us: a particle velocity, ID, age, lifespan, drag, mass, and particle force. So all these attributes are used to physically simulate those particles. And we are going to build a physics simulation, and it makes a lot of sense to use this pre-built ParticlePOP then, which is really amazing. Just like the feedback loops you are used to, you will have some kind of feedback end back here, and we are going to assign this as the target particles update pop. So this is now the iteration loop that it is going through, and we can connect this to our rendering back here to see something happening. Let's have a look at the little warning we see, and apparently rotate attribute and scale attribute have not been found. But they existed before, but apparently all those new attributes have been created for us by the ParticlePOP, but the rotation and point scale don't exist anymore. So let's have another look at the ParticlePOP, which we all go to a lot. So I'll color this in. And on the attributes parameter page of the ParticlePOP, we can choose to keep the rotation and point scale attribute and kind of copy those over to the points that are generated by the ParticlePOP. Yeah, speaking of points being generated, we should also talk about this. So the ParticlePOP doesn't just copy over the input points. As far as I'm concerned, I could actually use any surface. So for example, a torus. And then the ParticlePOP would actually generate particles on the surface of this input geometry. But if we give it an explicit point cloud, it will generate points from this point cloud. You can set the maximum number of particles. This can be quite high for us because, yeah, this is far lower than our GPU's maximum particle, than what our GPU can handle, let's say it that way. And we can give it a birth rate. So this is how many particles are spawned, in this case, per second. So currently there are 10 particles spawned per second. And if I set this to be higher, you can see how there are now more particles spawned per second. And there are some options to choose how it reuses points that later die off, and how it handles those freely available particle IDs and stuff. And if you want to randomize the input points or take them in their incoming order and stuff, not really relevant for us today. So let's move on in what parameters we have available here. We can set the expected lifetime in seconds. So if I were to set this to 1, all those particles would just live for 1 second and disappear again. But they are supposed to live for a while. And right now, all particles live for 10 seconds. If we introduce some life variance, some of these particles will live for 10 seconds, but some will live shorter, and this is somewhat randomized. And I think that's, just more interesting as well. And from here on, we kind of get to the physical part of it, because we can now introduce an initial velocity. So as I said, we have the particle velocity and particle force, particle drag. All of this sounds a lot like physical values being simulated, and that's the case. The ParticlePOP comes with a built-in physical simulation solver, which is amazing. So you can, for instance, just set an initial velocity of, let's set in -1 here. So now newly created particles just move downwards, and they don't have any acceleration or force that they feel right now, and there's no drag or something. They will just keep on moving in that direction. That's okay, but maybe not so interesting because they all move in the same direction. But I will leave it for a second. Oops, now I moved them upwards. And you can set the initial drag, which, if I set it high enough, you will see how they feel some drag force and are accelerated down if they go through the void. And velocity damping similarly just stops their movement after a while. These are some very handy parameters we have at hand here, but we'll not use this for our simulation because we are going to somewhat simulate space, and there's not really that much drag or velocity damping in space. So I will set all this back to 0, and instead we will work with the in-between of the ParticlePOP's feedback now. There is this particle force, and if things move around and change their velocity, that is always due to a force they feel. And TouchDesigner has set it up for us such that we can just set the particle force to any value for each individual point here. We could, for example, use a MathPOP and connect it in here. The MathPOP is similar to the MathTop and chop, as in we can just do some simple math on an input. And for pops, we can actually choose the attribute we want to do some math with, and we're going to use the particle force. And we could actually choose the parameter size, because the particle force is 3-dimensional. It's a vector. We could choose to do math independently for x, y, and z. Alternatively, we could also say that, well, I'm going to keep the parameter size at 1 and just do particle force.y, such that now we only do math on the y component of particle force, which is pretty great as well. Nice UI from TouchDesigner, I must say. And now we can change this particle force. It might be helpful to use a pop to chop here as well. Sorry, pop 2. And drag and drop this pop, and we can set the attribute scope to include particle force to have a look at the actual values. And this is just 0 for all of them. So let's add a little bit, like a small value to particleForce.y. And now we see how they move upwards, but in a different fashion than before, because now they are not spawned with an initial velocity and just move at that speed, but they are actually spawned with zero initial velocity, and then they are accelerated by this particle force. So this is actually simulating gravity. If we were to set a negative value, this is maybe a more reasonable or more expected behavior when it comes to gravity. So they are spawned with zero velocity and then they are accelerated downwards. So this is already pretty much gravity, because gravity, at least close to Earth, is somewhat felt like as a constant acceleration. And we can have a look at the top value that, of course, changes if we change the particle force here as well. Okay, so much about this math, this really simple math pop. But now let's create the more interesting behavior we are looking for, because we want to simulate gravity, but not just gravity downwards, but we want to calculate gravity towards a central point. So we should maybe make up our minds how we can actually formulate this. And I've opened the Wikipedia gravity page here already. You can read through this, but there's actually a formula given to us that is there to calculate the force an object feels based on its own mass m, and the kind of second mass m prime, which it is accelerated towards. And the formula is g, which is a constant, the gravitational constant, so we can kind of ignore it or set it to our artistical liking. But the force is proportional to the factor or the multiplication of the two masses divided by the square of their distance. So I think this formula should hopefully not be too intimidating for you, and it is feasible to implement this in POPs without any code. You can actually do a lot in POPs without code. So let's go ahead. The math POP actually is not sufficient for that, but there are two other POPs for mathematics. One is MathCombine. This is basically the most complex one, and where you have the most freedom. In the math mix, which is somewhere in between. I think it's fine to just use the MathCombine for now, which allows us to do everything we need. So instead of using the math pop here, we are going to use the MathCombine, and you by default are directly prompted to the combine parameter page. And here we can see that we can choose from a long list of mathematical operations, all like equipped with A, B, or C, or potentially all three of them. And we can just do stuff like A plus B, and then we can set the scope for A and B and choose how to combine those. So in this case, we could do A plus B, where A is the position and B is, I don't know, the particle's rotation. This doesn't make sense at all, but now we are in each time frame adding the rotational value to P. This completely breaks our simulation, but this is how we define those combinations. We choose which operations, and then we choose the attributes we want to do those operations on. On the input page, we can actually also choose to get attribute values from secondary inputs. We might connect a sphere here and then choose values from that. We might actually go ahead and do something like that later, but I think it's good for now to just work with uniforms, because we will calculate gravity for each point towards, or like gravity between each point and a central point. And we need to define that center somewhere. And it's reasonable to define the center as a uniform here of type 3. So this is the center position, center P maybe. and I will give it a value of 0, 0, 0, which is going to be the very origin of our space here. And we will also need the U center mass. I'm calling this U something such that it's easy to understand later that these are uniform values. Uniform values are values that are that have the same value for all incoming incoming entities, whether those are point attributes, vertex attributes, or primitive attributes. But whatever we set here is going to be this uniform across all of those. You can actually create new values on the MathCombine new attributes if you want to. You can do some free operations already, and then you can do all those combine operations. Let's have another look at the formula, and we will have to calculate this fraction here. So m times m prime divided by R2. We can definitely start by calculating m times m prime. So we are going to look for A times B, and this is going to be the particle's mass times the center mass. And I'm going to create a new attribute here, which is called the, I would just call it F, but F is not final here because F also includes this division by R2 and potentially multiplication by some factor. And F, well, I'm going to call this small f because eventually this force is going to be a three-dimensional vector. It's going to have a strength, but it's also going to have a direction attached to it. While what we are prompted here on Wikipedia actually is just one-dimensional. It's just the strength of it, and then we need to set the direction to be from our particle's position towards the center position. So this is going to be called f. Maybe I should just call it a fraction. That's the fraction that we're calculating there. So it's going to be particle mass times center mass, and then we are going to divide this by r squared. But first we need to come up with what r is. Now r is going to be the distance between our particle's position and the center position. To get that distance, we can first calculate a vector that is pointing towards our center position from our particle's position. So you can always just drop these down or write the name in here as you please. And this is going to be the direction. If you are not familiar with what I've just done here, calculating a directional vector from A to B by subtracting those, you should probably maybe watch a good YouTube video on the topic of linear algebra for computer graphics or something. But there are tons of good videos out there that explain why this is a reasonable operation to choose here. So this is basically a vector pointing from each individual particle towards my center. And I can now use the length combination operation, the length operation, and use this newly created direction as the scope. And the result is going to be called R. Then in the next step, we can do the A times A operation. And this is going to be R squared now. So it's just taking R times R. And then we can update our fraction by doing A divided by B. So we are going to divide whatever our fraction has been so far by R squared. So now this is our new fraction. And you can really think of this going from the first operation downwards, one after the other. So this is now we've calculated this whole term here, which is great. We now just need to also get multiply this by the direction. Now we do have the part of the force strength, but we need to get the force direction. You might be right in thinking direction is something we already have. It's just not normalized yet, but this direction should be normalized first. And we can actually use the normalized operation on direction. Alternatively, we could have divided direction by r, but let's use the normalized operation to get normalized direction. Let's just be explicit with our names here. And then we can multiply A times B. That is our fraction. So the strength of the force with the direction of the force. Whoops. Wow, what just happened? Interesting. I don't know where that came from. We are going to multiply the fraction, so the strength of our force, with the normal direction, and the outcome is going to be called gravity force. And this doesn't have an effect on our particle system yet, because the particle system itself works with the part force. So we should output to that by maybe getting the current particle force and adding the just calculated gravity force to it. Let's see what happens. Okay. The particles move somehow. I will restart the simulation and see that we get some issue because direction has not been found. Aha, I did a typo. Direction. Here you go. But maybe I again back to direction. Okay, direction. Yeah, okay. I did one typo once and then it screwed it over. Here we are. Let's save this because we came quite far already. This is maybe a little bit yeah, fast for sure. So we could reduce the speed of our ParticlePOP, how fast this whole system is simulated, or we can reduce the center mass. That way the gravity is proportional to that, so we can also scale down the, sorry, I lost my camera's position. I should delete this camera and work with a proper camera viewport. That will be easier, and use this as my camera and set the camera's panel comp to be parent.project, which is the top level container, and set the backgrounds over here to 1. And now I can actually go and perform one and look around. This is better. Okay, so we do have this gravity force calculated now. It's not quite the behavior you saw at the very beginning of the video, but we're actually not too far off. What is still happening now is that the particles are spawned with 0 initial velocity, and then they are just accelerated towards that center. But remember that our force strength is divided by the distance between those points and actually squared. So if that distance gets really small, the strength of the force gets insanely big. So the particles are just accelerated really, really quickly towards infinity and they fly off. And what is rather happening in our solar system, etc., is that they start with an initial velocity. So maybe I could set this to be 1. So the particles are spawned flying into a certain direction. I will reset the center mass to 1 as well. So they're spawned flying upwards now, and then they are drawn in towards that center, and then they actually go into this kind of loop here, which is already maybe better because they are not really accelerated too quickly, but it's also not the arrangement I was interested in. I don't want to use an initial velocity. I will pause it for a second, but instead I want to create my own initial velocity that is perpendicular to the particle's position. So if I maybe not use a circle, but rather a circle, but not the volume of the circle, but the surface only, I get particles that are spawned only on the circle, not on the full disk. And now I want the initial force, for example, of this particle to be the upwards direction. So if a particle lives here, it should be accelerated that way. If a particle lives here, it should be accelerated that way. We hence need to create this initial velocity ourselves. We cannot use the initial velocity that is generated by the particle pop because we can only set a constant initial velocity. How are we going to do this? Well, we can actually use the fact that the point generator comes with a normal attribute, and if we have a look at how that looks like for each point right now, we can actually turn on the viewer, right click, and choose to display attributes of a pop with in different ways, either as text values, as vectors, dots, or colors. And we're actually going to look at the normal vector as a vector. And we get all those arrows. Actually, we're getting too many to really see any of those arrows. So I will reduce the number of points to 100 for a second. And you see that the normal actually points outwards. And that is a good starting point for what I want to achieve. I will turn off this visualization again. But we can actually use this because together with the transform pop, where we chose not to transform geometry, but to transform an attribute, and that attribute is going to be the n, we can rotate this, and yeah, the output is going to be my velocity val. If I display velocity, we now see that velocity is just the outwards facing normal that we started with, but I can now rotate this vector around z, so this blue line, this blue axis. And if I do so, I can actually rotate them by 90 degrees, and then my newly calculated attribute points exactly in the direction I wanted it to point in. So I'll turn this off again, reset the number of points I wanted to work with, and go to my particle velocity, ParticlePOP, because now we want to use this initial velocity that we created here. So the velocity, we want to use this as the initial velocity. And to do that, we can go to the map page of our ParticlePOP and choose the incoming velocity as the element and the parameter that we want to map this to as the initial velocity. And now we see how all those particles are actually spawned at their respective positions with an initial velocity that is tangential to the circle, and they are then still feeling that gravity force, but because the mass is exactly 1, the math that we've set up here results in this exactly circular motion. If we were to reduce, or maybe I will increase the center mass to 2, and you can see that now the acceleration does not exactly match the incoming speed in the way that they stay on their circle, but they now actually fall in towards the center, and then it looks like they are all in this circle, but if I reduce the number of points here dramatically, you can see that those individual points, they are actually flying on ellipses around the center. So that's what we are actually seeing here. And yeah, that's the behavior we expect. And we can change around the center mass to, well, we can already create a quite interesting pattern by animating this, I guess. But this is looking promising, I think. But we need to create some more, need to make it more interesting to get the result I was looking for, because right now all those particles are spawned at the very edge of this circle. I will use another transform pop on, well, this one I can really transform geometry. And, oh, sorry, I didn't want to use the transform. I wanted to use the random and use the multiply combine operation with a random size of 1. And this is just going to multiply my particle's position by a random value between whatever it shows here, between A and B. And as you can see, by doing this, I can decide to either have all my particles on the outer ring or actually scatter those particles in this disk. Here we actually see some pattern in the randomness, and that is because the seed of this random pop is the same as from the point generator. So let's choose some different seed, and then there's no pattern visible anymore. And yeah, good. This is already getting closer to the visual I was looking for. We could spawn more particles at the same time. And now we do get this swirling pattern. I like the swirling system. What I don't like too much is that they are still all living in this disk or like in this one plane, because they are all spawned in that plane and only feel a force in that plane. We could either move the center position up and down a bit if we want to, and then they would still, like, if we could actually animate this, and then those particles would scatter around, not only in that plane but all throughout space. What I want to do instead is use yet another random pop, and I will use a random size of 1. And I want to add something to the initial velocity that we are creating here, which is currently the initial velocity is also in that XY plane, and I want to add something to velocity.z such that the particles are spawned with a certain, like the particle's velocity. Let's have a look at this. If I have this value at 0 as well, you see that the particle's initial velocity is all as well in this plane. And if I add some velocity here in velocity.z, those arrows will also leave that plane, so they start with the velocity that is not only in that plane. Maybe I want this to be between minus some value and plus that value, such that they move up and down as well. And I will turn off the viewer. So this is already more interesting. I like it way more. We could potentially work with even more boxes if we feel like it, and I think it would be more aesthetically pleasing to reduce the speed of the simulation a bit. And then this is already getting closer to the result we were looking for. Maybe we want to set the random point size a little bit higher, so some of those boxes are actually bigger. We are also currently not assigning any material to our geometry, and I would like to use a PBR material here. I will need to reduce the metallicness and maybe the roughness a bit, and then increase the light dimmer. But I think we can achieve a better or more interesting look using the PBR material, maybe together with the environmental light. So let's get some HDRI map. Oh, I'm here in my HDRI pictures folder. Let's get to this, copy parameter, paste value. Yeah, now we are in the default samples map, so you can actually follow along because you also have this collection of images. Let's just use the cloudy ocean as our environment light and maybe reduce its brightness. It's dimmer, but yeah, this is maybe already looking far more interesting. Cool. I think it's not really too visible right now, but if we restart the simulations, you will see that the particles, they just appear out of nothing. And if they die off after their lifetime, they actually also just pop out of existence. And I think that's not too pleasing. What I would like them to do is that at birth, they just scale up. And then if they die, before they die, they just scale down such that they, slowly appear and disappear again. We can do that by altering the point size of the boxes based on their age, on the particle's age. We do have the particle's age somewhere here, particle age, and we do have the particle lifespan. And together with that, we know what fraction of their total lifespan they've already been through. So using a math combine again, here we can divide A by B, where A is the particle's age and B is the particle's lifespan, and this would be the normalized age, which is now going to be between 0 and 1. So if the age is 0, it's 0, and if the age is lifespan, it would be 1. And that value, normalized age, we can use to look up into a lookup curve, which we can create using a curve pop. So something like this, but I would like to add a second segment to that curve that ends at 0 again. Oops, like this. And then using the alpha and beta values here, we can design the size of our particles throughout their life. So my idea is that they quickly get big if they are born, and then shortly before they die, they just get smaller again. So this is the lookup curve we will use. And then we can use the lookup attribute pop to do so. There's actually also a lookup channel and a lookup texture. The channel you can use to look up into a chop, and the texture to look up into a top, which is great for all kinds of stuff. But right now we are going to look up into this curve. So I connect it to the second input, and I will connect the math combine where we calculated the normalized age into the first input. And then let's connect this into our chain here. As a lookup index attribute, we are going to use the normalized age. The index range is going to be between 0 and 1. That's the idea of the normalized age. Yeah, we do want to interpolate. Actually, the rest of this is not really relevant for us because we calculated the normalized age specifically for this purpose, and it will be between 0 and 1 already. And we are going to look up the curve value that we created here, which is actually equivalent to p.y, but we are going to look up the curve value, and the output attribute scope is going to be, well, we could use point scale, but this value goes from 0 to 1, so the new point scale would also be between 0 to 1. We don't really want that. We want to scale the point scale. So let's introduce a new attribute here called point scale scale. Let me know if you might have a better idea for a name of that attribute. And then in the next math combine pop, I will do A times B, and I will multiply point scale by point scale scale. Yeah, so if we start the simulation again, you will see how those particles smoothly transition in and out of existence. And that's what I wanted to achieve. And yeah, I'm pleased with the result. I hope you like it. There's a lot you can build off of this, and this tutorial was mainly to be understood as an introduction to POPs and a little bit about how you can simulate physics in POPs. And I think it's amazing that a big part of that is done behind the scenes using the ParticlePOP, and you can introduce your own forces into the system and everything. Yeah, I think it's just pretty amazing that POPs come with this built-in particle simulation tool for you. And I hope you learned something today, and I'm curious to see if you create something based off of this tutorial. If so, please tag me in your post so I can see what you're doing with this. I would be really interested to see that. Okay, so thanks a lot and see you all soon. Bye bye.